Well, let me continue with vertical stress distribution. In the last few lectures, I have discussed various methods by which we can find out the vertical stress at any depth. Actually, if I apply the load at the surface at a depth z, we have shown in the very beginning that different types of stress will be there. There will be vertical stress, there will be horizontal stress, tangential stress, shear stress, all those things. Those are there, but we are interested now for the time in vertical stress only, and that magnitude is quite high compared to other, and most of the loads are vertical, and it will give because of this vertical load settlement takes place. So, many a times we need to find out the magnitude of vertical stress at any depth, and we have discussed different methods. And now, one by one we will try to see the application, that how to apply how these methods will be applied in different areas. So, one problem is this, first problem is like this, the base of a tower consists of an equilateral triangle frame of 6 meter each, on the each corner of which the column of the tower is supported. The total weight of the tower is 600 kilonewton, which is equally shared by all the 3 columns. Compute the increase in vertical stress in soil caused by the loads of tower at points 5 meter below any one of the columns. So, this is the problem. That means, we can imagine that there was a tower with a equilateral triangle. The end points are triangle. So, the column, one column is here, another column is here, another column is here, and then finally, the total load carried by. So, I will not take total each, it will be the total weight is a total weight, okay, 600 kilonewton, which is equally shared. So, that means each will be 200. So, this will be 200, here also 200, here also 200. Now, we have to find out vertical stress at 5 meter below any one of the footing. So, below this footing or below this footing or this footing. So, we can very successfully apply the Bouguen's point load formula here, because these 3 footings, they are all equal distance. So, if I find out because of the loading at this footing, what is the stress at 5 meter below, that we will find out. Because of this loading, what is the stress at this point, that also I can find. This, in that case, that become R. And third one, again this is the loading, and because of this loading, what is the effect here, that also I can find out, but this and this to this will be similar. So, that means, I have to find out once for this and then once for this, and if I, because of symmetry, I can find out this plus twice this. So, this is the problem, just application of point load formula. I will just show you in the calculation steps. The plane sheet. So, this is the one. Suppose we have equilateral triangle. This is a one footing, this is another footing, this is another footing, and it is 200, this is 200 and this is 200, and it will be this will be formula will be, when I will be, this is 1, 2 and 3 suppose. So, footing 1 to 1, suppose this is the first I will do. In that case, R become 0 and Z become 500 and Q equal to 200. So, our formula is delta sigma Z, suppose 1 equal to 3 Q by 2 pi Z square 1 by 1 plus R square by Z square to the power 5 by 2. Since R is 0, this part become 1. So, ultimately, because of this, it will get the value. So, 3 into 200 divided by 2 into 2 multiplied by pi multiplied by z is 5 square. So, this gives you the value. I have taken actually 600. So, it will be 1/3 whatever value I have got. So, let me give you the correct value. This will be 11.459 divided by 3. So, it will be 3.81. This will become 3.81 kilonewton per meter square. Okay. So, now similarly 2 to 1, when putting 2 effect on 1, you can consider, in that case your R will become how much? R become 6 meter, because this is equilateral triangle of side 6 meter. So, R becomes 6 meter, Z is 5 and Q equal to again 200. So, you will be again applying the same formula. Suppose I say this is delta sigma Z 2. In that case, you will see 3 into 3 multiplied by 200 divided by 2 multiplied by pi multiplied by 5 square, same depth, are 1 plus r square, r is 636 divided by z square 25 to the power 5 by 2. So, if I calculate this one, whatever value will get, that is whatever I have got here, it will be just divided by 3. So, I will find out that. So, it will be 1.232 divided by 3. So, it will be 0.410. So, and 3 to 1, it will be again same, r equal to 6, z equal to 5 and q equal to 200. So, this is same. So, delta sigma z 3 will be equal to again 0.410. So, total delta sigma z equal to 5 meter will be equal to your 3.81 plus 0.41 plus 0.41. So, 0.41 plus 0.41 plus 3.81. So, it will be 4.63 kilonewton per meter square. So, at 5 meter depth below the any footing. So, since they are symmetrical, from here to here whatever distance, here to here whatever distance. So, if we calculate here, it will be same here, it will be same here. So, any below any footing at 5 meter depth, the pressure will be 4.63 kilonewton per meter square. So, this is the first application, and second one, 9 square footings of equal size, that is 2 meter by 2 meter, arranged in a square pattern, 3 in each row and 3 in each column. Each footing carries 60 kilonewton load and center to center spacing of the footing is 3 meter. Determine the vertical stress at a depth 5 meter below the center of one of the corner footing. So, here I think I have taken some wrong data. So, center to center, according to whatever calculation I have done, if I do, then now I will be taking instead of 3 meter, according to calculation data I have taken, actually spacing is 1.8 meter. So, if I take this, then it will be better. So, it is not 3, suppose the problem is 1.8 meter spacing. So, accordingly I will just show the calculation, the steps. So, what is the, based on the description, what it is saying, you have 9 square footing, one is this and this and this. So, 9 points. So, 3 in each row and 3 is in column in a square pattern, and this distance suppose is 1.8 meter. everywhere, center to center distance is 1.8 meter, and each footing carrying a load of 60 kilonewton. So, I have to find out determine the vertical stress at a depth 5 meter below the center of the one of the corner footing. So, this is the footing, corner footing, or this is the corner footing, this is the corner footing, this is the corner footing. So, this corner footing at center 5 meter below. So, if I find out any of the corner, it will be same. So, I will try to show based on this corner suppose and show the calculation. So, this is the correction you have to take. Footing size suppose not known anything, it may be 1 meter by 1 meter, and spacing is 1.8 meter, that is the thing to be taken. So, based on this if I do the calculation, then if I do the calculation, then I will have the footing like 1, 2, 3, these are 9 footings. I can number it 1, 2, 3, 4, 5, 6, 7, 8, 9, and I can calculate. Suppose 1 to 1. So, that means this is a footing 1. So, 1 to 1 effect will be there, from footing 2 to 1 and 6 to 1 will be same. So, I will calculate only 1. Similarly, 3 to 1 will be there and 7 to 1 also will be the same, I will calculate that, and then 4 to 1 and then 8 to 1 also will be same because of symmetry, and 1 to 5, 5 to 1 and 9 to 5. So, that means one calculation for these two, one calculation 2, this and this, one calculation 3, this and this, one calculation 4, this is one 5 and 6 calculation will be there. So, I will show 1 to 1, in that case r equal to 0 and z equal to your z equal to 5 meter and q equal to 60, and in that case your delta sigma 1 will be 3 into 60 divided by 2 pi and z actually 5 square. So, that gives you, because r is 0. So, second part will not be there. So, it gives you 1.146. Now, 2 to 1 or 6 to 1, that is same. In that case r will become 1.8, r become 1.8, z is same 5 and q is same 60. So, in that case I will get your delta sigma z sigma 2, suppose I will give the name, then in that case 3 multiplied by 60 divided by 2 pi z square 25, 1 by 1 plus 1.8 square divided by 5 square to the power 5 by 2. So, this calculation if I do, I will get a value equal to 0.845, it is giving you 0.845. And now, 5 to 1, suppose this 5 to 1, in that case r become under root 1.8 square plus 1.8 square, because this and this distance 1.8 and this is 1.8. So, that become 2.545 and z equal to 5, q equal to 60. So, then you have delta sigma z 3 suppose, or I can say z 5, since footing 5, then it will be 3 multiplied by 60 divided by 2 pi 5 square 1 by 1 plus 2.5545 square divided by 5 square to the power 5 by 2. So, this gives you value equal to 0.644, 0.644, and now I will do this is becoming 5 to 1 and then 3 to 1, 3 to 1, that means 3 to 1 and 7 to 1, 7 to 1 both are same. In that case R become 1.8 plus 1.8, this is 3.6, Z equal to 5, Q equal to 60, and then if I delta Z 3 if I say, then your calculation will be 3 multiplied by 60 divided by 2 pi 5 square 1 by 1 plus 3.6 square divided by 5 square to the power 5 by 2, and this value will be coming equal to 0.403, 0.403. And next is I will take new one, I will take another, that is 8.1 and 8.1 and 4.1 both are same, and in that case your R will become 3.6 square plus 3.6 square under root. So, that be 3.6 and 1.8, sorry, 3.6 1.8 square, okay, and that will give you 4.025, and Z is same 5 and Q also same. So, if I apply, so this is becoming suppose sigma 4 del sigma 4 and 3 multiplied by 60 divided by 2 pi 5 square 1 by 1 plus your 4.025 square divided by 5 square to the power 5 by 2, and this value will come 0.329, 0.329, and now another will be there delta 6 9.1, then there will be 9.1, 9.1 actually R become under root 3.6 square plus 3.6 square and equal to, it is 5.091 and Z equal to same 5, Q equal to same 60. So, once again I can calculate delta sigma sigma, suppose this is this, I can write 9. So, that become 3 multiplied by 60 divided by 2 pi 5 square 1 by 1 plus 5.091 square divided by 5 square to the power 5 by 2, and this value gives you 0.193. So, these are the different components I have got. Suppose one footing here, 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 one footing here. So, I get for 1, then for 2, so plus 2 into 2 and this is 3 and this, so plus 3 into 2 and this is suppose 4. So, this and this same. So, plus 4 into 2 and this is 5 only alone and 9 also and alone. So, all to be added. So, if I do that, then I will get delta sigma will be equal to 1.146 plus 0.644 plus 0.193 plus 2 into 2 multiplied by 0.845 plus 2 multiplied by 0.403 plus 2 multiplied by 0.329. So, that gives you 5.5 5.137. So, this is the way. So, that means this corner I want to find out. So, I will found because of this putting what is the pressure at here, because of this putting what is the pressure here, because of this putting what is the pressure here, similar this is because of this putting what is the pressure here, because of the putting what is the pressure here, like that I have to calculate. And because of symmetry I have reduced the number of calculations I have done for one, I have done for this, I have done for this. So, I have done this means I have done already this, I have done this means I have done this, I have done this and then this one and this one. So, 1, 2, 3, 1, 2, 3, 4, 5, 6. So, 6 component added. So, and some of them twice. So, I have got 3 single and 2 twice. So, this is 5.137. So, this is the value I will get. So, this is the one of the application of point load. So, there generally in the building there are number of columns and they will be symmetrically placed, and because of the one column what is the stress in the other column, sometime approximately will find out and check whether there is overstress or not. So, this is the way one can calculate. So, now I can go to third application. Third application is something like this. An annular footing with inner and outer radius 6 meter and 8 meter respectively is supporting a tank which exerted a pressure intensity of 200 kPa. Determine the pressure increase at a depth of 5 meter below the center of the footing because of the foundation pressure. So, what is the problem here? Problem is here annular footing, that means there was a footing of annular footing means it is a circular footing can be there, is an entire solid, and annular footing means it is between two circular areas. Suppose this is the outer radius and this is the inner radius. So, this is actually footing, this is footing and rest of the part actually hollow. So, if this portion is loaded, these portions are loaded, then what will be the pressure at this point? There will be pressure below this of course, but what will be the pressure at the center we are interested. So, that is we have to find out that too at the center of the footing and at a particular depth, that is depth is given here 5 meter. So, to find out this let me see the calculation procedure. So, as I have shown that annular footing, this actually I can do by applying method of superposition, and you can see it is given radius of 8 meter with outer radius and 6 meter. So, this is suppose 8 meter, and suppose I assume this entire area is loaded with intensity q, then at 5 meter depth delta delta sigma 5 I can delta sigma 5 I can find out. There is a by integration for circular footing at the center we have done q multiplied by 1 minus 1 by 1 plus r square by z square to the power 3 by 2. This is the formula we have derived. Now, this in this problem, since it is not a full circular area loaded, so it is only partly loaded. So, initially I am assuming the entire circular area loaded with q intensity, and in that case what will happen, I am getting some pressure and of course, the entire area was not loaded. So, I have to do something to get the actual effect. So, if I assume first the 8 meter radius of the footing and r equal to 8 and z equal to 5, and if I put in this equation, then I will get a delta sigma 5, and that means delta sigma means pressure increase at a depth 5 meter, and that will give you some value that is equal to q. Q is given something, I will see that q into 1 minus 1 by 1 plus r is here actually 8 meter square and z 5 meter square to the power 3 by 2, and this if I simplify, then I will get 0.85 q, and q suppose I do not know right now. So, q fine at the end I will multiply with q, and now this is the one, this is the outer radius. Now, I will consider another circular area, this one small, or I can do in the same circular area this one. Suppose this one is loaded now, then I can actually again find out another delta sigma z or delta sigma 5 for other circle. So, that will be equal to q 1 minus 1 by 1 plus r is here actually 6 meters. So, 6 square divided by z is 5 square to the power 3 by 2. So, that gives you a value equal to that is 0.738 0.738 q. So, since this one initially I have considered this one, I am now suppose I want to remove this, I suppose I consider this is upward loading negative, and if I consider that, then I can consider this as a minus. So, initially I have taken entire area, and now I am multiplying, I am subtracting this one, this effect, then that will be used minus sign. So, if I do minus sign, then ultimately your net sigma z or z is 5 here will be equal to, initially we have got 0.85 q minus this will be 0.738 q, and then this will be, if you do 0.112 0.112 q, and that gives you q is given I think 200 kPa. So, if you multiply by that, then it comes 22.4 kPa. So, this is the finally the value. That means, I will be when this type of I know the circular area loaded at any depth along the center of the footing, I can find out the pressure by using this formula, but when there is annular formula, what I can do? I can take initially entire solid and then I can subtract this one. So, that is the thing I have calculated, this is with plus and this is minus. So, this minus this become this. So, this is another application. So, like this I have so far covered these two aspect, that means how to use the point load formula, how to use the integration formula for circular area, then rest part actually how to use corner formula, how to use approximate formula, that is trapezoidal distribution. Those things I will be showing in the next application. Thank you.